Hello, this is Joseph Ryan Bernicki with Dr. Osbay's High-Speed Aerodynamics course, and today we're going to be simulating a flow through a CD nozzle, and we're going to have two cases. We're going to have case one, where we're going to have a shock in the diverging section of the nozzle, and we're going to analyze the differences in the variables across the shock, such as pressure, temperature, density, speed of sound, Mach number, velocity, and we're also going to plot XY graphs of all those same variables as well. So, and the plot is going to be based off of a center line going through the middle of the nozzle. So, first off, we already built our geometry in Design Modeler. It was a pretty simple geometry, so I didn't feel the need to go into SolidWorks to build it. For the next project, I will, or for the bonus assignment, I will, because I have to add in a wedge, but that's for a later date. So this mesh is simpler than the mesh that we did previously. It's a little less refined in the middle because I was having troubles with Ansys going through and finishing up the simulation and getting the convergences that we, or the getting to converging, getting the residuals that we need. So we still included the inflation in this. However, we are going to be running an inviscid model for simplicity's sake, just to really focus in on the shock and what happens with the variables as it goes across. So models, we have energy on, we have inviscid. For materials, we had to change it from ideal gas or we had to change it from air to ideal gas, and that's because air had a constant density, and this is going to be a density-based model as shown in our general tab right here. So density-based, absolute, we're going to do steady, not doing transient. So we're going to do ideal gas for the density reason. And then the cell zones, we don't have to mess with that other than going in here and we can go into operating conditions. And we're just going to zero everything out. We're going to go into gravity. We're going to zero everything out. Operating temperature, we can leave as is. Specified operating density, we can go ahead and zero that out as well. So, okay, that's all cool. Fluid, we don't have to worry about that. Ansys will auto set that. Once you're going in and you're making your mesh, you can do your name selections. If you need to look at how to do name selections, I have the other videos. But it's really easy. You just select the edge, right click, names, create name. And then monitors, residual. We're going to want to go in and change everything 1e to the -6 because it is set default 1e to the -3, but we want to refine it a little bit more. So we're going to go ahead and change that. Boundary conditions, we need to make sure we have our pressure inlet, not velocity inlet, because we're dealing with high speed and we're dealing with compressible flow. So we need a pressure inlet. We need the internal will set itself, and more importantly, we need the pressure outlet. So in the case one that we're studying here, we're going to have a shock inside the nozzle. So to do that, we are going to have an elevated back pressure, and we're going to have about 3 megapascals in the inlet. So after that, we're going to go ahead and we can go into initialization. Now for this, I did standard initialization. I computed it from the pressure inlet, and I just initialized it from there. Most of the tutorials I watched had hybrid initialization, but I found that standard initialization worked better for me. And it came out with better simulations when I was doing it from the pressure inlet. So that's what I did. This simulation has already been ran through, and the Mach number, go right here. As you can see, we go into a supersonic flow after the converging section that transitions with the bow shock here into the diverging section, and we get the supersonic flow, and we can see here the shock. And then after the shock, we get a drop of the Mach number into subsonic flow again. So this is exactly what we were expecting, exactly what we wanted to get from this simulation. And then after that, we can also see that the velocity is going to be correlated to the Mach number. We see an increase in velocity up until the shock, and then it decreases immediately after. And then the other variables are actually going to drop, though. Over the shock, we're going to see a drop in the temperature. Or I'm sorry, we're going to see a rise in the temperature. It's a drop in velocity and Mach number. It's a rise in the other variables. It's a rise in temperature, pressure, density, and speed of sound, because speed of sound is a function of temperature. So go ahead and you can see we can display speed of sound. I don't know what that error noise was, but so we're going to go ahead and display speed of sound. And yeah, we have the rise in speed of sound because we have a rise in temperature, and then we have a rise in static pressure as well, and a rise in density across the shock. So, and then you can also see in the XY plots here, it's just going to be plotting that same, we're going to have the speed of sound is going to drop, and then it's going to rise directly after the shock, dramatically. And we're going to see the same thing with temperature, because speed of sound is a function of temperature plot. And then for velocity, we're going to see the reverse though. We're going to see an increase and then a drop after the shock. But and Mach number as well is going to be the same as velocity. But the shock was it was a fun simulation to do. It took me forever to get the balance between the pressures to actually get the shock to stabilize in the nozzle during the simulation. But it's really cool to see it visualized in this way. So we can go ahead and exit out of this one and hop into our case 2, which our case 2, I just had the mesh data plugged right into the setup because it's the exact same simulation. We're just lowering the back pressure and allowing the shock to flow out. So we can go ahead into our solution here, edit that. And again, I've already ran these simulations through because especially with the shock, it was I've clicked don't show this message 30,000 times and it always shows the message every single time. Now, graphics. Okay, so, and like I was saying, this mesh is exactly the same as the last simulation. The only difference is we dropped the back pressure. All of these settings are exactly the same. Let's go ahead and look at our contours. Yeah, so exactly as we have talked about in class, the Mach number is going to increase up until Mach 1 in the converging section. And then we're going to see a further increase into supersonic flow throughout the diverging section. So you can see the bow shock here, but since there is no normal shock present in the diverging section of the nozzle, we don't see the drop in Mach number. We just see it continue to increase until we hit the exit. So we see it increases all the way up to 2.39, Mach 2.39. So we're going to see the same relation between velocity as we see here in Mach number because they're directly related. Temperature, though, we're going to see a continued decrease in temperature because we don't have a shock, so there's nothing that boundary is not there to shoot the temperature back up and decrease the velocity. So we're just going to see a steady decline in temperature, and then with temperature, since speed of sound is a function of temperature, square root gamma RT, we're going to see it does the exact same thing. So let's go into density. Density is going to decrease throughout the entirety as well. Let's go into, what are we missing? Static pressure. Static pressure decreases as well as the velocity increases. So with the plots, it's going to be the exact same thing as the last ones, except it doesn't have the jolt in one direction from the flow experiencing the shock and having the set of variables on the other side. So we just see a slow decrease in the speed of sound, and we should see the exact same thing for temperature. And then we're going to see the steady increase in velocity and Mach number. And then decrease with the density and the static pressure as well. So these simulations did exactly what the theoretical knowledge was telling us they should do, that we've been learning in class. It was a lot of fun. The shock was difficult, but it was definitely a rewarding one because of how much time I put into messing with the pressures and trying to get everything to work and actually get it to stabilize. So it was a lot of fun. Either way, thank you very much. I suppose that is all. Have a great rest of your day. Goodbye.